Okay, so we've covered some of the most basic things concerning sets. And the next thing we want to do is talk about operations that you can perform on sets. Just like how with real numbers, you can take two real numbers and add them to produce a new real number, or subtract them, or whatever operation you want to do. There are operations that we have defined on sets. In other words, how can we take two sets, perform an operation on them to create a new set out of them? And the two primary operations we want to talk about, although there are plenty more than these, the two that concern us are intersections and unions. And again, this is probably something that you are familiar with from previous classes. So if you have two sets, A and B, we define the intersection of A and B to be the set with this notation. So it looks like an A, an upside down U, capital U, and a B. That's the intersection symbol. We define this to be another set that contains only the elements that both A and B have in common. Okay, so in other words, another way of saying that is X belongs to the intersection of A and B if and only if X belongs to A and X belongs to B. That "and" is important, okay? A union of sets is defined a little differently. So if we have two sets, A and B, we define the union of A and B to be the set of elements. Notice the union notation uses a right side up U. You could just think U for union. It's the set of all elements that are either in A or in B. So in other words, we can say, we can write this: X belongs to the union of A and B if and only if X is in A or X is in B. So we have an "and" here and an "or" here. What that means, you can think of the union as a larger set, because it's the set that contains everything that you would get if you threw A and B into one giant set. So let's do an example. Okay, here we have set A, and it's a finite set, has 5 real numbers in it, 5 odd numbers, 1, 3, 5, 7, and 9. And then we have B. This is not a finite set. Notice the square brackets. That makes this an interval of real numbers, including its endpoints. What would be the union or the intersection of A and B? Well, the intersection should contain only the elements that belong to both sets simultaneously. Now notice A contains the numbers 1 and 3, but these would be outside of this interval because they're smaller than 5. However, this interval does contain 5, 7, and 9 because those are numbers that are between 5 and 10 inclusive. So 5, 7, and 9 are the only numbers that these two sets have in common. That makes this their intersection: 5, 7, 9. Okay? What about the union of A and B? Well, now we're not looking for things that the sets have in common anymore. We're just looking for everything that belongs to either of the sets. So notice B, like we said before, contains everything from 5 to 10, which is already accounted for here. What does B not contain? Well, it doesn't contain the numbers 1 and 3. So the way I can write this union, I have to continue using a union symbol. The union is the set of numbers containing 1 and 3, as well as everything between 5 and 10 inclusive. Notice, because I used this union symbol here, this accounts for everything that belongs in either A or B. There's not really a simpler way to write this, so I have to continue using the union symbol in this case. Okay, moving on. Here, we want to prove a basic property of sets. So we want to prove that for any sets, A and B, regardless of what they are, the intersection of those two sets belongs to A, and it also belongs to B. Or in other words, the intersection of A and B is a subset of both sets at the same time. And then it asks, does a similar relationship hold between the sets A and B in the union? And that I'm going to let you think about and answer on your own. I'm not going to answer that one here. So remember, in order to prove that something is a subset of something else, we have to pick an element of the thing that we expect is a subset, and then show that that element belongs to the larger set over here. We sometimes call this a superset. So I want to let x be an element, any element, of the intersection of a and b. This is where we resort to a definition. What does that mean? Well, that implies that x belongs to both a and b at the same time. But, more specifically, if x belongs to a, then that right away shows that the intersection of a and b is a subset of a. Because of this property, if x belongs to b, and x was chosen arbitrarily from their intersection, then that would also mean that a intersect b is a subset of b. So that proves both of those properties simultaneously. Okay? Moving on, we're almost done talking about sets. So, one more thing is an important definition that we'll use from time to time. If A and B are sets, and the intersection of A and B is the empty set, then we say that A and B are disjoint. What does that mean? Well, if the intersection of two sets are the empty set, then that means that these two sets have no elements in common. If they did, whatever elements they had in common would be in this set, but the empty set contains nothing. So this is a way of saying that A and B have no elements in common. Okay? Notice the empty set notation became useful for that definition. So here's an example. If A is the set of negative real numbers and B is the set of positive real numbers, then A and B are disjoint because there are no numbers that are both negative and positive simultaneously, which means A and B have no common elements. All right. Moving on, we're going to do a quick discussion of functions. Now, functions are discussed in great detail starting in algebra, and then you expand on those in calculus, and it's a central topic in all of mathematics, the topic of functions. For us, because this is something you should be very well versed in, what a function is, I want to introduce some notation that you may not be familiar with because it's going to be important to what we do in this class. So I give the formal definition of a function here. Technically, if you want to go to the formal definition, functions are defined to be sets. We actually define them as sets of ordered pairs. And they satisfy this property. If x1 and y1, if x1, y1 and x2, y2 are ordered pairs belonging to this set that we're calling a function, then if x1 equals x2, that implies that y1 equals y2. Basically, what that property does is it guarantees that if you have the same input, it can't give you two different outputs. That's the defining characteristic of a function, informally speaking. One input should only ever give you one unique output. Okay?